What if you could cut your journey time in half, gliding at speeds beyond 500 kilometers per hour while effortlessly floating above the tracks? This isn't science fiction, but Japan's Chuo Shinkansen, a maglev train project set to revolutionize travel between Tokyo and Nagoya. With an estimated cost exceeding $82 billion, it's one of the most expensive infrastructure ventures in history. Unlike conventional trains, this futuristic system uses magnetic levitation for a smoother, faster ride, drastically reducing travel times and cutting carbon emissions. However, despite its promise, construction delays, budget overruns, and environmental challenges have cast doubt. Can Japan's bold vision deliver on its ambitious promises, or will it falter under mounting obstacles? Beneath Japan's dynamic urban landscape lies an urgent problem: congestion and travel inefficiency. Major travel routes are increasingly gridlocked, leading to frustrating delays for commuters and significant economic losses. As populations grow and economic demands rise, the existing transportation systems struggle to keep pace. The renowned Shinkansen network, once the pride of Japan, is now grappling with overcapacity, failing to accommodate the rising number of passengers. The need for a revolutionary transportation solution has never been more critical. In the early 1970s, Japan began its exploration of magnetic levitation, Maglev Technology, envisioning a faster, more efficient rail system. This ambitious endeavor culminated in the construction of the Yamanashi test track in 1997, marking a critical milestone in the development of superconducting maglev. After years of rigorous testing and refinement, the construction of the Chuo Shinkansen officially began in 2014. This new line aims to connect major cities, covering 438 kilometers predominantly through tunnels. The first phase of the project is expected to link Tokyo and Nagoya by 2027, followed by an extension to Osaka targeted for completion by 2037. This maglev system will reduce travel time between Tokyo and Osaka from 2 hours and 30 minutes to just 67 minutes, greatly enhancing business and tourism opportunities. The Chuo Shinkansen stands not only as an engineering marvel, but also as a testament to Japan's competitive spirit in the global race for high-speed rail. Currently, China's Shanghai Maglev is the world's only operational high-speed maglev, but Japan's system is set to surpass it in both distance and speed, reaching 505 kilometers per hour. Moreover, Japan's L0 series maglev even achieved a record speed of 603 kilometers per hour in 2015. Economically, the maglev is poised to transform Japan by linking Tokyo, Nagoya, and Osaka into a cohesive metropolitan hub. This integration is expected to attract investments and generate an estimated economic impact of up to 17 trillion yen over the first 50 years of operation. Additionally, the line's efficiency will appeal to tourists, allowing them to explore Japan's iconic cities within a single day. While constructing this advanced network involves substantial costs and extensive tunneling, nearly 90% of the line to Nagoya will be underground. It reflects Japan's ambition to create a faster, safer, and more resilient transportation infrastructure. Designed to withstand earthquakes and provide a seamless travel experience, Japan's maglev project aims to not only transform domestic travel, but also inspire similar innovations worldwide. As it evolves, this groundbreaking train could serve as the blueprint for next-generation rail systems globally. But what innovative technologies and engineering feats are being employed to make this ambitious vision a reality? At the heart of the Chuo Shinkansen is its innovative use of superconducting magnetic levitation (SC Maglev) technology. Unlike traditional high-speed trains which run on rails with wheels, the maglev train floats above the track using powerful magnets. These magnets generate lift and forward propulsion, eliminating the friction that usually slows down rail vehicles. The SC Maglev trains hover approximately 10 centimeters above the track, allowing them to reach unprecedented speeds while maintaining energy efficiency. The principle of magnetic levitation involves a set of powerful magnets on both the train and the tracks. These magnets work in opposition to one another, creating lift that pushes the train off the ground. A second set of magnets on the track generates a forward thrust, pulling the train along. One of the key features of the Chuo Shinkansen's design is the figure-8 configuration of the coils along the track. This arrangement helps stabilize the train, keeping it centered and balanced even at high speeds. Stability is particularly important in Japan, a country prone to earthquakes, making the system's safety features a top priority. Building this maglev line requires an immense amount of engineering expertise. Much of the track will be underground, with nearly 90% of the Tokyo to Nagoya route running through tunnels. The largest of these tunnels will cut through the southern Alps, reaching depths of up to 1,400 meters. This 25-kilometer-long tunnel alone is one of the most complex and challenging segments of the project. Drilling through Japan's mountainous terrain requires precision and careful management of geological factors like groundwater and seismic activity. The use of specialized boring machines ensures that the excavation is both efficient and safe, reducing the risks of collapse or other accidents. Building stations for the maglev system adds another layer of complexity. One of the key terminals, Shinagawa Station in Tokyo, will feature 4 tracks and 2 platforms, all underground. Constructing a new station underneath a city that already has one of the busiest train hubs in the world presents a delicate challenge. Engineers must carefully plan every stage of the process to avoid disrupting the existing Shinkansen and subway lines that run just above the planned maglev platforms. This involves drilling, reinforcing, and ensuring that the structural integrity of the surrounding infrastructure remains intact. The tracks for the Chuo Shinkansen are designed to optimize speed while maintaining safety. For instance, the minimum curve radius is set at 8,000 meters to allow the train to maintain high speeds even on turns. Additionally, the gradient can reach up to 4 degrees, helping the train to climb steep slopes found in Japan's mountainous regions without losing momentum. The propulsion and levitation systems built into the tracks are powered by a series of electromagnetic coils. These alternating electromagnets interact with superconducting magnets on the train, creating a thrust that propels the train forward through linear induction. Essentially, the entire track becomes a motor that drives the train, a process that is highly efficient but requires precision engineering. Maintaining the superconducting magnets is a challenge in itself. To achieve the required magnetic levitation, the magnets must be cooled to extremely low temperatures. Liquid helium cools the superconducting coils to negative 269 degrees centigrade, maintaining their superconducting state. A specialized cooling system known as a pulse tube refrigerator is integrated into the train to manage temperature fluctuations efficiently. This technology is adapted from aerospace applications, underscoring the advanced nature of the project's design. Energy consumption is another crucial factor. Although the Chuo Shinkansen is expected to use 30% more energy than the current Shinkansen network, it is still more energy efficient than other modes of transport over similar distances, such as short-haul flights. The maglev system generates some of its energy through regenerative braking, which converts kinetic energy back into electrical power when the train slows down. This system reduces the train's overall energy consumption and makes it more sustainable. One of the most pressing technical challenges is managing the electromagnetic fields generated by the maglev system. The powerful magnetic forces that lift and propel the train create electromagnetic fields that could potentially interfere with passengers' electronic devices, or worse, pose health risks. To address this, engineers developed shielding made of electric steel to protect the passenger cabins. This shielding redirects the magnetic fields away from the train's interior, ensuring the safety and comfort of travelers. Despite its innovative technology and ambitious goals, the Chuo Shinkansen project has faced numerous obstacles. Delays have become a significant issue, particularly due to environmental concerns in Shizuoka. The prefecture's opposition to the project has already pushed back the planned opening of the Tokyo-Nagoya route from 2027 to 2034. Negotiations are ongoing, but the project's future depends largely on resolving these local issues. JR Central has committed to continuing its efforts to find a compromise, but there's no guarantee that construction will proceed smoothly.
新幹線は今東海道新幹線が走っているこの地帯は大変災害が予想されるところなので、そういう災害に強くするためにバイパスを作るというのが第一の目的ではあるんですが。
Safety is another major concern. A tragic incident in October 2021 highlighted the risks involved in such a complex project. 2 workers lost their lives when a temporary retaining wall in one of the tunnels collapsed. This disaster prompted the organization to intensify safety protocols, ensuring that all construction sites undergo thorough checks and that workers are protected from potential hazards. With so much riding on the successful completion of the Chuo Shinkansen, they cannot afford to compromise on safety. One of the significant challenges in tunneling through such terrain is managing the environmental impact. Digging deep tunnels disrupts natural water flow, and there are concerns about how this could affect local ecosystems. Shizuoka Prefecture, through which the tunnel will pass, has been particularly vocal in its opposition. The Oi River, which provides much of the region's water supply, could experience a drop in levels due to the diversion of groundwater during construction. After years of debate, the company behind the Chuo Shinkansen proposed mitigation efforts such as controlling dam releases and providing compensation for potential losses, though these measures have not fully eased local concerns. Cost is also a factor that looms large over the Chuo Shinkansen. The total project budget is estimated to exceed $82 billion, making it one of the most expensive infrastructure developments in Japanese history. Financing the project involves a combination of private investment and government loans, with expectations to recoup some of the costs through future passenger fares. However, with such a hefty price tag, there are concerns about whether the line will be profitable in the long term, especially if delays continue to push back the opening date. Ticket prices are expected to be only slightly higher than those of the current Tokaido Shinkansen, meaning that the margin for profit is slim. The Chuo Shinkansen is a bold venture that showcases the potential of superconducting maglev technology to revolutionize high-speed travel. Its groundbreaking design, from the electromagnetic propulsion system to the deep tunnels under Japan's southern Alps, represents a leap forward in transportation engineering. However, the project's many challenges, including environmental concerns, safety risks, and financial hurdles, pose significant obstacles that must be overcome. Whether the Chuo Shinkansen can meet its ambitious goals will depend on how well these challenges are managed in the coming years. The world is watching, and the future of high-speed rail may well be determined by the success or failure of this remarkable project. If you enjoyed this video, please like, comment, subscribe, and turn on notifications to stay updated on our latest content.